In part A of the AP problem, we are asked to describe two features of the graph that's given, and that would help identify HA as a weak acid. So in the graph, the initial pH of the weak acid is 3, which is greater than what the initial pH of a strong acid would be. Also, the pH is greater than 7 at the equivalence point. If it were, say, a strong acid, strong base solution, the pH would be 7 on the dot. In part B, we are asked to describe a method to find the value of Ka for the weak acid. So at the halfway point, pH is equal to pKa, and since pK and Ka have a similar relationship to pH and H+, we can do 10 to the negative pKa value is equal to Ka. For part C, we are asked to sketch a titration curve for 25 milliliters of 0.10 molarity HCl instead of 0.10 molarity weak acid. And so it would look like the blue line, so the pH starts at 1, and then going to 25 milliliters, the same amount titrated as the weak acid. This time the pH is 7 instead of more than 7 though, since the strong acid and strong base neutralize each other. In part D, we are told that a 25 milliliter sample of 0.1 molarity weak acid is titrated with 0.2 molarity NaOH, and part 1 asks what volume of the base must be added to reach the equivalence point. So we can find the millimole value of the weak acid, and we know that's equal to the NaOH at the equivalence point. So we can take 2.5 millimoles of the OH minus and divide it by the molarity, and that gives us 13 milliliters. And for part 2, we are told that the pH at the equivalence point for this titration is slightly higher than the pH at the equivalence point in the titration using 0.1 molarity NaOH. And this is because the volume at the equivalence point for 0.2 molarity NaOH is less than that of the 0.1. The smaller volume means that molarity of the conjugate base will be higher. This will make the pH value higher.